plot the graph between the shear stress and the velocity gradient in case of different kind of fluids. So x-axis goes for velocity gradient and y-axis goes for shear stress, right? So as we have seen in the previous video, in case of Newtonian fluids, it just follows tau equals to mu du dy, but for non-Newtonian fluids it's tau equals to a du dy to the power n plus b. For dilatant, n is greater than 1 and b equals to 0, so it's basically tau equals to a du dy, right? And here n is greater than 1, so it's basically increasing curve starting from 0. So it's like this. And in case of Newtonian fluids, it's tau equals to mu du dy, so it's basically linearly dependent on the velocity gradient. So this is Newtonian. This one is dilatant. Then comes Newtonian. In case of pseudoplastic, b is 0 and n is less than 1, so basically it will be a decreasing curve like this. This is pseudoplastic. Now in case of those materials, as we just stated, for whom b is not equal to 0, the shear stress will start from a certain value. This is called tau 0 or initial stress. Just as we stated in case of being a plastic, that these fluids always have a certain minimum shear stress before they yield. So in case of thixotropic, n is less than 1 and b not equal to 0, so it will be like this: n is less than 1, reducing curve, but b not equal to 0, so it will start from a certain value. This is thixotropic. And then in case of rheopectic, b not equals to 0, but n is greater than 1, so it will be an increasing curve like this. So this is rheopectic. And in case of ideal plastic, where b is not equal to 0 but n equals to 1, so it will be a linearly increasing one, and this is called ideal plastic. And in case of ideal fluid, where there is no internal stress in case of velocity gradient, it will coincide with the x-axis. This is called ideal fluid. Here basically A is 0, B is 0.